So whenever we are given delta G naught, looking for K. Just plug and chug, be so careful of your units, so careful of units. I avoid errors if we're still in this packet that was on your desk, Jacob. I'm so sorry if that's I plug and chug into here and then do the inverse natural log. That helps me avoid errors. All right. So let's solve for K just like we did when we were finding hydrogen ion concentration. Inverse natural log. Do you call it e to the x? Yeah. There you go. And it matches with what we predicted. Yes.
It's
so much wood. Thank you very, very much. Thank you very, very much. So yeah, when you do natural log, it increases inverse natural log. Thank you, Grace, so much. Yeah, you're exactly correct. Thank you. I'm so careful. I know that we can see if we didn't do, conversion. And of course, you could have converted this to joules. Totally your call. And you don't have to show metric conversion. Okay. Could we take a look at this yellow equation sheet? All right, this would be like the thermodynamic equation. Okay, if we take a look at the one below it, delta G naught is really a standard because it's so incredibly rare that we're going to have 1 molar solution. So incredibly rare if that's what we're dealing with. So most times, reality delivers a delta G, non-standard delta G, which we would interpret the same way, negative, positive, etc. We need a correction factor if we're not at standard conditions. I hope that makes sense. All that we're expected to know is, okay, if it has the floating zero, what does that mean? If it doesn't have the floating zero, what does that mean? We are not asked to apply that equation. But it's actually from this equation that we get this. All right. So if you want to cross that out. All right. If we could go to our packets. Still have that smaller packet that you got at the beginning of class. Okay. So page 29 in your unit packet. So if you're ever perusing through this and thinking like, oh my gosh, we didn't cover this. It's been adjusted. I forgot to remove these pages. So 29, nope, because it's asking us to apply that delta G equation. Nope. And, oh, sorry. I gave us the work for that. And then, oh, we could solve 31, just saying, but, and 33, nope, no worries there. We don't have to apply that equation. And 34, nope, these are just extra problems I've given us. But I think we're good from there. Yeah, we definitely are. Okay. Could you turn to page 40, please? Page 40. All right. I do not mean to insult your intelligence. I hope this isn't too much of an insult. Can we take 40 seconds and fill out this table? Joey, could you read across what you have here?
Negative products greater than 1.
Fantastic. Next.
Positive reactants less than 1.
Other J.
0 equilibrium 1.
I guess. In neither. Yeah. Or I'm so sorry. What did you say?
Equilibrium.
Yeah. And 1. Yes. Good. Okay. So I think we need to do these middle. So if in a situation, the enthalpy is negative and the delta S is positive, what sign will we have on delta G? Negative all day long. What does that mean? Thermodynamically favored. Yeah. If delta H is negative, that means exothermic. Delta S being positive means an increase in positional probability or number of microstates. So both things are in our favor. If we're being grounded by this equation, negative, positive, then this term will be negative, makes this negative. So the reaction is driven by both H and S. And it doesn't matter what temperature. So any temp, it'll be thermodynamically favored. So that is the best scenario. What would be the worst? Now, of course, it just means we have to add energy, so it's not tragic. The opposite of these, huh? Yeah. So if this is positive, this is negative, that makes that term positive. Not thermodynamically favored. This would be endo. If delta H is positive, this is decreasing positional probability. Temp has no impact. Okay, so if it's exothermic, So that's in our favor. But here, we're decreasing positional probability. Abrielle, what do we want then with our temperature to make this negative? If this is going to be negative and this is going to be negative, do we want low temperature, high temperature? And then it'll be enthalpy driven. Does that make sense? We say enthalpy driven or entropically driven, entropy driven. And so then it will be the opposite for this situation. So this is in our favor, not this. And so we want high temp. So then your entropy prime. Yeah. All right. How are we feeling? Free response, multiple choice. Let's see, who's Olivia? Free response, multiple choice. All right. Can we go back to the little packet? And we just found our K value. So if we turn the page, we will talk about that on the AP Chem exam. There are 60 multiple choice that you'll tackle first. You're given 90 minutes. So it average about a minute and a half per question. 60 questions, 50 count. They try 10 for future exams. We never know what the 10 are. And we'll keep practicing that. All right. Then the free response portion are 7 questions. The first 3, they call them long, just because they take a little longer. Usually that absolutely will involve calculation. And then there's 4 short questions. A long question could take between 20 and 25 minutes, and a short, about 10 minutes. So we'll practice. This was question 2 from last year. So this is an example of a long question. All right. Now, don't ever worry if it's not for you, but the first part of a free response is to like get you to breathe and not stress. So it's easy. Oh, go ahead.
Mr. Lazy says A is easy, B is harder, C is impossible for like stat.
Really? No, not with us. No. So you definitely want to keep looking, because if you forget some, no, not with us. The only thing that sometimes happens with multiple choice, the first one is going to be, yeah, because it like lets you get your breath. All right. In a free response. But the multiple choice, traditionally the first 5 are easy. And then like the last 2. And then it ebbs and flows. So truly, I wish I had like a better thing to tell us. All right. So here, given a reaction, now we can't overlook anything. We're given the enthalpy. All right. I want to make sure. Oh, I see I have a catalyst. Who knows if that will be important. All right. Are the hydrogen atoms oxidized or reduced? It's good for us to just remind ourselves of that. And they want us to justify. So CER. Anybody want to share? and CH3OH. Hydrogen is showing it's always oxidation number. Oxygen, -2, unless it's in peroxide, and you will be told that. Hydrogen, always +1, and it'll be +1 there. And then we're making, so I just do a little squiggly, or you could do a full reaction arrow. It's just recognizing it's not a balanced equation. To H2. What is the oxidation number we assign to hydrogen here? Big old 0. An element in its element form. Big old 0. So we went from +1 to 0. Ger or Leo? Gain electrons reduction, lose electrons oxidation. So how do we go? We needed to add electrons, yeah? So, and it's okay if it's not balanced or anything else. So it is reduced. Hydrogen as reactant. You know, I like to, is making as product. Or reduction, something like that. Okay. Lewis dot. Yay. Carbon, nitrogen, oxygen, fluorine always have their octet satisfied. Always. They do not go over. Excuse me. Oxygen only needs, it comes in with its 6 valence. It only needs 2 more shared with it. But carbon needs 4 more shared. So I think we can easily get a double bond. Yeah. We'll never have lone electrons in the structures that we do. So I'm going to pair them up. It doesn't matter where we pair them. Hey, carbon needs 2 more, but we can't give any more to oxygen. A coordinate covalent bond. Oxygen, electrons are electrons. So oxygen, its energy is lowered by sharing that additional pair. Why not? So a triple bond between these. Just a reminder, triple bond is the shortest, double bond a little longer, single bond the longest. Why? A single bond is a sharing between the plane of the nuclei, where a double bond is a sigma and a pi. And so they need to come closer to get the overlap of the p orbitals, and then a triple even closer. So just a reminder. Don't worry. Spend time reading. Oh, but you know what else we could say? What is the hybridization on carbon? So we count up the number of electron areas. It's a blending of our orbitals. So we have 1, 2 areas, sp hybridized. And we just looked at bromine. So the question is, what is the hybridization on bromine? 1, 2, 3, 4 electron areas, 1, 2, 3, 4, sp3. Anyway, we'll go over that. Okay, now the rest is thermodynamics. Any questions before you go ahead and tackle part C, I, and II? Okay, dig in. Yes, sir.
Aren't you canceling moles?
Yes. So, absolutely. Thermodynamic terms, whenever they're applying to the entire process or reaction, they often have this mole reaction that's put back on. So, strictly obeying the equation, yeah, we're canceling out moles. But then to show, well, this is for the process, we put mole reaction back. Yeah, so that's just something for us to know and not be shaken by. It's telling us it wants that. So as soon as, because this is like per mole of CH3OH, per mole of CO. So now it's per mole of the reaction. Yeah, and we just assign that back. Is that okay? Yeah, I know that. Yeah, that's a little weird. Any questions? Have to be up. Yes, ma'am.
You just put, like, nodules per mole would be a place off the mole reaction.
No, that would be accepted. That would be accepted. I would just be, since they're specifically telling us, yeah, I'm sure that it would also fly, yeah. If you just put kilojoules, the kilojoules per, yeah, then we're okay. Yes,
Since they gave the enthalpy value as 3 sigfigs, would our answer have 3 sigfigs?
see, but what, here? Or in the previous?
Yeah, on the previous page, they gave the delta enthalpy as 90.
Right, but we use these values, and so, and you're subtracting and adding.
Okay.
And so when we subtract, we're bound to the least precise decimal place.
Okay.
So that's why I showed that there. And then, oh, silly me. But then we're okay to go to the 10th. I'm so sorry that I didn't do that. 0.0. That's too quick work on my part. Thank you for asking me. All right, that is our chapter. That's it. That's it. So to round us out, could I ask us, thank you, Olivia, for making the choice for your response. Could we find okay. I lettered these pages. So beginning with page N. Okay, a collection of model choice. And I'd like us to focus on the ones that I have circled. Now I have one circled on the other, but this is worth our time. So 3, 4, 5, 6, and then I think there's 2 more. Oh, a couple more. So can we go ahead and take, and let's just see how far we get by 9:08, and then we'll share the answers. So the number 3, D. Number 4, B. Number 5, A. Number 6, C. And 16, C. 18, not sure if we got this far, I'll go ahead and share. 18B, 19A, 20C. Just to go and address, so what's going on is a step by step of how solid elemental potassium would react with 1/2 mole of chlorine diatomic to make that. That could be enthalpy of formation, just saying. All right. So, I mean, somehow potassium needs to become a +1 cation, and chlorine needs to become a -1 anion, starting with these. So these are the step by step. First, sublimation. You know that's going to be endothermic. Then ionization energy required to remove an electron. Then we're breaking the chlorine-chlorine double bond, that's bond energy. And then electron is added. Ooh, that's going to be a release. Closer an electron is to the nucleus, the lower in energy it is. And then, whoa, this is the payoff. When the cation and anion, Coulomb's law, lattice energy, when we've created an ionic compound. So anyway, that might help with those concerns. Do you want to talk through which Yes. I'm sorry, sir.
Or
Oh, sure. All right. Okay, so make sure. I am so guilty of not closely reading everything you're given. We're told, oh, it is thermodynamically favored. So then we know delta G. It becomes unfavorable at high. Okay. So here's when things are not going to cooperate as we would hope. And so unfavorable at higher temperatures, well, then that must mean that's negative, which is going to make this, when this is big, positive. So, is that all right? Have a good rest of your Tuesday.